Other side. All right. So let me get people in. I got 3 people. 4 joining us remotely today. Interesting. There are actually a lot of people joining us remotely. Oh. All right. All right, so I think I got everybody in, from Zoom, so we can get started. All right, so first thing first, I do want to remind people that there is a allowance of 3 remote participation. Okay, so people who are actually participating remotely now really need to kind of understand that part. So 3 remote participation without excuses, and an excuse would be a doctor's note sent to me prior to the lecture where people want to participate remotely. So I do want to make sure that that part is clear so that people don't just go like, oh, you mean from here now I can just remotely participate in this class? The answer is no. Okay, so I will move that out of the screen here so it doesn't interfere with the actual recording. All right, so today's focus is going to be CNF because you have a homework assignment due in a week that is on CNF or conjunctive normal form. And then before we do this, I just want to remind you guys that exam 1 has been graded. Your score is in Canvas, so you can check your score. That is adjusted already. I think the 3rd highest score of this class was 3.75. So your original score has been multiplied by 4 divided by 3.75 already. So what you see is the actual score that will be recorded as a part of your final score. Is that okay so far? I will add, the reason why points are taken out and whatnot when I do have times, because I do have a full description of exactly where points were deducted and for what reason. I have your exam. I have not scanned the exam yet, so I cannot pass it back to you. But if you have any questions, I'll be more than happy to make photocopies and send it to you. So this way we can talk about why points were deducted. Is that okay so far? All right. All right. So what we'll do today is to talk about conjunctive normal form, which is the first step that we need to use, that we need to understand before we can prove theorems using the modified version of propositional calculus. All right, so the first thing is to show you an example, because I don't want to use the homework example, the homework assignment as an example, because otherwise I'll be doing the homework, which defeats the whole purpose of the homework. All right, so I'm going to switch to Joplin, which I think is started already, and use this as an example. Okay, so this one is pretty easy, but I want to show you the steps, okay, of how to do this. All right, so go ahead. I got someone on Zoom who's asking a question. Okay, I guess that was not a question. All right, and I can chat my chat channel too. See if anyone is trying to talk to me. Nope, there's no chat activity whatsoever. All right, so and I will double check that we are actually recording. Oh, the question is there anything here that I don't know? Well, I would not know that, would I? If I know that, it'll be kind of creepy, because it means I am not only a mind reader, but I'm a remote mind reader. Kind of like, Darth Vader being able to do the Force choke thing remotely. So I guess he is really remote manager. In a very dark sense, yes. All right, so getting back to you. All right, so we want to convert P or Q implies not as into a CNF, into its conjunctive normal form. Now, we have already talked about what is CNF, right? So a CNF is a gigantic conjunction, typically, of junctions. And then inside each disjunction, we can have variables, or we can have negated variables. But those are the only two things we can have in a disjunction. And then the CNF itself is a conjunction of these disjunctions. So that's what we talked about already on Monday. So what we'll do is to talk about exactly how to get this one done. Okay, P or Q implies not S. Now, in this case, I specifically did not include parentheses because I want you guys to kind of think about this and go like, okay, so what is that implication implying? Are we looking at P or and then open paren, Q implies not S, or are we looking at open paren, P or Q, close paren implies not S? So that has to do with operator priority. And in the homework assignment, let me switch back to the homework assignment here. So in the homework assignment, I also specify here, the priority of operators from high to low. So that means, this means negation or boolean negations has the highest priority. You always apply negation to whatever immediately following the negation operator. So if it's a single variable, it applies to that single variable. If it's an expression in parentheses, then you apply it to the expression in parentheses, okay? The next one is conjunction. So conjunction is has the next highest priority. It is kind of like between conjunction and disjunction, their relationship in terms of operator priority is similar to multiplication versus addition. Addition has lower operation priority compared to multiplication. So that means in the absence of parentheses, you always perform the multiplications first, then you perform the addition. When we're dealing with Boolean expressions, we always perform the conjunctions first, then we perform the disjunctions. But in this case, we also have a fourth level in terms of priority. This one has the least priority, which means in the absence of parentheses, implication is always done last. Is that okay? Are we doing okay so far? All right. So in terms of notation, because I don't want you guys to have to learn how to use LaTeX or to use the equation editor for all those actual symbols. So that means we're going to use these operators. For negation, we're using exclamation point, which is what you use in C++. We use multiplication. Sometimes you don't even need to have the asterisk to represent conjunction. And then we are going to use addition for disjunction. And then implication is just equal to greater than, okay, because that looks like, the right arrow, okay? So that's how we can, so this way you can use a plain text editor in Notepad to work on this homework assignment. You don't need a special editor to do all the equation, all the special math symbol stuff. So are we doing okay so far in terms of the priority of operators, as well as what symbols you can use to represent Boolean negation, conjunction, disjunction, and implication? We're doing all of, okay, so we're good with that. All right, so what I'll do next is I'm going back to Joplin. Okay, there we go. So we're going to get back to, we are going back to Joplin. And then we look at the expression that we have, which is this one here. So the first thing I'm going to do is to change it so that it becomes the easier format, that you can just type on keyboard without using the LaTeX notation. So, on the left-hand side, I'm using backtick, because that means it's verbatim. It's good for, representing just, code and stuff like that. So in this case, we have P or Q in parentheses, implying the negation of S. So if I want extra parentheses, this is basically what it is. And you guys can focus on the right-hand side instead of the left-hand side. So this is the starting point. The question is, how do we turn this into a conjunctive normal form? There are two ways to do it. The first way is very mechanical. You basically make a truth table out of this expression, and then you pick out all the rows in the truth table where you get zeros, and then you convert each row that you see a zero into a DE or a disjunctive element. And then the conjunction of all those DEs would be your CNF. Okay, I will do that. Okay, but I want to give you an idea of what it looks like first. The second way is to do it using boolean algebra. So you basically derive the CNF. Okay, so with this example, we'll do both. Okay, and how you want to do your homework assignment is up to you. Okay, so you kind of have to look at what tools you have available and what you're good at in order to determine which way you want to do it. So the first way in this case is to use a truth table approach. So we'll go look at the truth table approach. And I do want to go back to the notes first so that you guys can find out, okay, so if I want to read about this, where do I go? So I'm going to go back to notes. We're in propositional logic. I did update this document here. So if you have printed this out or if you have downloaded a version, you might want to do it again because it has been updated. Like earlier today. All right, so if I go down to the completeness of CNF, it does have a long discussion of how to do the conversion. So for those of you who want to understand the mechanism of the conversion, you can read all this. What I'll do today is to explain it while I'm presenting the exam. In the survey that was conducted earlier this semester, there was a written feedback. They crossed out the course code as well as the name of the professor. So they only said that this person has some comment on CISP XXX regarding Professor XXXX. But from the comment, I know it was me. Because I cannot think of any one of my colleagues, teaching in any class that is, focusing on the theoretical aspect, because the student was saying, I cannot understand how things are applied, because this professor only talks about the theoretical aspect, the abstract aspect of things. So right away, as soon as that word abstract appears, I know it had to be me. So anyway, so I'm trying to change that by presenting the concept as I go talk about the method, the actual example of doing it. So there we go. And don't worry, because if you are the person who wrote that comment, I cannot know who wrote it. Okay, so no worries there. Because that's important. That's always important to make sure that students do not feel that they can potentially be threatened by the professor. All right, so truth table. Okay, so we'll do the truth table approach. So in this case, the truth table would have how many rows? In other words, how many variables are we dealing with here in this expression? How many do you count? 3. Very good. So with 3 independent variables, how many rows do we end up in the truth table? 8. 8. Because 2 to the power of 3 is 8. Every variable can be true or false, but whether one variable is true or false has nothing to do with what the other 2 are doing. So that's why we have 2 times 2 times 2, which that's giving us 8. Okay. So when we perform this truth table, so just kind of deal with this for now, and then we have the expression itself, which is P or Q. The whole thing implies not S here. All right. So I'm making a truth table using Markdown. And if you have time to kind of play with Markdown, it's actually quite useful because that's how people comment projects in GitHub. That's one big application of Markdown, but it's also a very concise way of formatting text. So I feel that it's not difficult to learn either. It's just a matter of okay, I don't quite know how to do this yet. I just need to look it up. Yes.
That are supposed to be in yes. That are yes.
R is yep, that's supposed to be S. Thank you. You can still have unrelated variables, but yes, that was intended. All right, so now we just need to create all the different rows. So I'm going to do the lazy thing. So to y, which is copy. And because we need 7 additional ones, so 7p. So now I just pasted the 7 rows of these things. And then we just need to give these values. So p can alternate between false and true. Like so. That's just one way to do it. And then q can alternate every 2 rows, okay? Because now we have 0, 0, 1, 0, 0, 1. And then S can alternate every 4 rows. So we have 0, 0, 0, 0, 1, 1, 1. So now we have the truth table. On this side, you guys can focus on the right-hand side because the left-hand side is going to look kind of messy at times. So now the question is, when P is false, Q is false, and S is also false, what is the value of the expression? It's going to be true because P or Q itself is going to be false. And as a result, as long as the left-hand side is false, the implication is always going to be true. So that means I have a little shortcut here that I can apply. Every time I see P and Q both being false, the implication is going to be true. So I can locate all the rows with that particular pattern. And there are 2 of those because this one is guaranteed to be true too. And then the rest, I kind of have to evaluate. Is that making sense so far? Okay, so now I have to look at the second row. The second row says we have basically true implies true. Why do we have true implies true? It's because P is true, so that means P or Q is going to be true. On the other side, we have the negation of S. S is false as a variable, so the negation of that is going to be true. True implies true, which is true. So to get this table worked out here, question? Is there a question from someone who's remote? If not, you might want to turn off your mic, or I can turn it off for you. There we go. So use the chat channel if you want me to re-enable your mic. All right, so now we are getting onto the third row. The third row is kind of the same deal because P and Q are both in the disjunction. So with this one, it is also going to be true. This is also going to be true. This is going to be false, false, and false. All right, so we do okay so far with the truth table at this point. Now, how quickly you can get the truth table done depends on a few factors. One is, are you doing it by hand or are you writing a program to do it? Now, with 3 variables, it's pretty easy to do it by hand, but your homework assignment has one that has 5 variables. The length of the truth table is exponential to the number of variables. So with 5 variables, there'll be 32 rows, okay? And then the second factor that depends, that determines how quickly you can get this done, has to do with how familiar are you with the operators, okay? Conjunction, disjunction, implication, and so on. So, it's up to you, okay? So, whether this approach works or not. Do we have any questions at this point? Okay. Yes.
Is this an implication, right? So false implies true is true. Wait, or false implies false.
All right. So how do we know, what implies what is true and what implies what is false?
And well, if it's a 1, it's true. 0.
You look up the truth table of implication. Yep, that's how you do it. Okay, you look up the truth table of implication.
And the only one that makes it is false implies true.
No.
It's true false.
True implies false is the only time an implication returns a value of false. That's important, okay? So at this point of this semester, I think, it is very, very important. If you cannot memorize, you should know where to find that truth table. It should be in your own notes, in a special section that defines the operators, okay? So, if it's just a recommendation, okay? To kind of make sure that you know where to find the definitions of the operators. Yes. Mhm.
If they're both true, does that, how does that work to make the left-hand side of the equation true?
Okay, so if you have that question, then you might break it down into smaller chunks. So the P or Q, P or Q is just based on the disjunction operator or. This is P or Q.
Oh, those.
Can we revert back to the original method we used? It's confusing.
It is? It's right here.
Oh, I see.
Yeah, so I'm using the alternate operators because this way I don't have to use the mathematical symbol to do this. Yep.
How did you select the columns for PQ and S? Why did you choose this method like 0, 1, and use attention to 2 rows and attention to 4 rows? Why did you choose that one?
I could have randomly make it, but I'm missing one row, wasn't I? No,
Scroll
no.
down. So
Yeah, it's scroll down here. There we go. Okay.
if you have 4, then for the fourth one we change the 16.
Yes, so if you add one more variable, you end up with 16 rows. For instance, if I have a variable t that I also want to take care of, then t would be 8 zeros and then 8 ones. And then the pattern of the other 3 variables would just simply repeat. So there are several ways to look at this, okay? One way for those of you who have taken a class that talks about binary numbers is this is just binary number conversion, okay? The first row is 0, the second row is 1, the third row is 2, and so on. And each variable or the value of each variable is basically a particular digit in a binary number. In this case, it would be a 3-digit binary number. So there are ways to generate this table, okay, using a tool. You can easily write a program to do it. With only 3 variables, how do you generate this table using a program written in C++? How long will it take you to make this table? If I just say the standard output needs to be something like this, doesn't have to be formatted exactly like this, but something like this. How long will it take you to write that program? I'll give you a few orders of magnitude. It will take you 5 minutes, 15 minutes, an hour, a day, or a week. 15 minutes would be a reasonable amount of time. If not 15 minutes, maybe half an hour. Okay, this is certainly something you should be able to do within half an hour. Okay, if somebody is looking at this particular problem and go like, it might take me a few days to do it. I would suggest that individual to come talk to me in office hour. I'm not kidding. I'm really thinking, if somebody is thinking this will take me more than an hour. Okay. So does anyone want me to kind of show you the corresponding code for something like this? Maybe. Guys? Yes. Okay, we'll do it. So we'll go ahead and actually do this one. Let me get to a terminal first. Now, how well this scale up to the problem that you're dealing with, that is up to you to decide, okay? Just because this code is easy to write does not mean it's easy to do the same thing for the homework assignment. Okay, so I will call this one, truth table tt.c. So I'm just using plain C here. We'll go ahead and count include standard file.h because I'm a little bit old school. I like to use printf instead of cout. Okay, it's the same thing. It's just syntactically it's a little different. And here's main, and I'll do it in the most intuitive way, which means it is not as easy to extend this, but it's more intuitive. So the most intuitive way to do this is to have the 3 variables. We got P, Q, and S. I skipped R for some reason, but it's okay. So P is going to start with 0, which is false. P is less than or equal to true. plus plus p, okay, this is a loop here. And I'm going to do the same thing for the other two variables. So we have q, we have r, q, r. This is one thing that's not good about copy and pasting code is if I forget to change one of these variable references, the program, oh, it's s, right? Yeah. I keep forgetting that I skipped a letter r. There we go. And we'll also get the indentations right. Okay. So now what do I need to do? I just have to use a printf statement here, which is print formatted. Okay, that's what the F stands for, is formatted. So if it's formatted, it depends on how I want to do this. I can just do a %d, 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 and one more %d. So each %d is representing a placeholder, and then the value for the placeholder has to be an integer, and the integer is going to be a part of the arguments following the format string. Okay, so that's basically what printf does. Now, printf has a lot of variants. It has a sprintf, which means it's not printing to standard output. It returns a string instead. Okay, so you can generate a string from a format string and the values to put into the placeholders. There are just variations of the printf. I personally think it's really easy to use, but some people disagree, but that's okay. So now we have your p, r, p, q, s here. So these three, okay, this p is going to the first %d, the value of this q is going to the second %d, this s is going to the third %d. So the last one is going to be the expression that I want to evaluate. So in this case, the expression is rather easy to express. So we have an implication. So every implication is the same thing as the negation of the first part or the second part. Okay, so this would be the left-hand side of the implication. So that would be just a P or Q. So I can just use the P or Q here. And then this side is going to be the right-hand side of the implication, which is the negation of S. And I'm just going to use the negation of S here. So obviously, in this case, in order for this program to only generate zeros and ones, I'm making the assumption that it's using one to represent true. So it may or may not be the case. So if I really want to make sure that this output is really going to be 0 and 1, I'm going to give it one more layer of parentheses and then say, if it is true, give me a 1. If it is not, give me a 0. So this will coerce whatever non-zero integer that the compiler chooses to use to represent true to just 1. Okay, and I think we're done. So how long did that take? You guys are going like, but I don't trust you. Remember that trust thing that we talked about earlier? You're not supposed to trust me. You're supposed to ask me to verify everything that I did. Okay, and also if it's better if you can do the verification, but if not, you're supposed to ask me and so go like, Tech, I don't know whether this program is going to work or not. Show me that it works. Okay, so we'll go ahead and do that. So save the code, gcc-ott.c. That's just a command line way of compiling the program and run the program. So the question is, are we getting the same thing? No, we are not. So that means, oh, it is probably the same thing. It's just that the zeros and ones are arranged differently here. So we can just, it's flipped. Yep. PQS. So PQS are these three. So we'll go ahead and check this 0 here. I think those are all correct. It's just that the ordering is different. We can just do a quick count of how many ones we have. We got 5 ones here. We also got 5 ones over here. So I think they are really the same. So that's one way to do it. So the next question is, but that doesn't look like a CNF here. Well, it's not a CNF by itself, okay, but it's getting close. So let's get back to Joplin to find out how to convert the truth table into a CNF. So I'm adding a new column here that I'm just going to call DE or disjunctive element. So if you don't know what a disjunctive element is, you might want to go back to the notes and read a little bit more, okay, because I refer to the term of a disjunctive element already in the notes. All right, so the first row has a value of 1. I have nothing to do here, okay? So any row that ends up with a value of 1 for the expression, there's nothing to do. Because I only want to do limitations based on the rows that return a 0. The reason why I only pay attention to the rows that has a value of 0 is because remember, we are trying to make a conjunction of things, right? So with a conjunction of things, as you add more terms to the conjunction, you are making it more likely to return a false as a result, okay? If the original conjunction is false to begin with, there's no way to turn it into true by adding more terms to the conjunction. But if the original conjunction is true to begin with, by adding additional terms to the conjunction, you can make it false. Does that make sense? Because it only takes one thing in a conjunction to be false for the entire conjunction to be false. So it's easy to turn things into false. It's impossible to turn things into true. All right. So now with this one, so what I need to do is to figure out a way to express this particular row so that this row and only this row is going to be false. All right. So how do we do this? So with this particular row, I'm going to use the right-hand side. So with this row, P is true, Q is false, and then S is true. I want that combination of values in the variables to give me a result of false. But I want all the other rows to be returned true, and only this row to give me false. And I want it to be a disjunction. So how do we do this? Okay, so we'll take a look at a so somehow we have to look at the disjunction that involves these three variables. The question is, how do we make this happen? Okay, so if I just look at P or Q or S, obviously that disjunction is going to be true because we have P and S both being true in this case. So the disjunction involving all three variables, non-negated, is going to be true, which is not what I want. I want the disjunction to be false, but only for this specific row. So what I need to do is, if a variable is true to begin with, I need to negate it first. If it's already false to begin with, if Q has a value of false in this row, I leave it alone. But since S also has a value of true, I also need to negate it. So now let's take a look at this new disjunction here and see if this disjunction is going to be false, at least for this row, and preferably for every other row, it should be true. Is that okay? So let's check it, okay? P is true, not P is false. Q is false to begin with. S is true, so not S is going to be false. So when you look at not P or Q or not S, that's going to be false, at least for this row. Does that make sense? But how about for the other rows? What do you think? For all of the other rows, at least one item in the disjunction is going to be true. And as a result, this expression here is going to be true. It's going to be false only for this particular row. For all of the other rows, it has to be true. Is that okay so far? Okay. So I'm going to do the same thing with the two additional rows that also got zeros to begin with. So with this one, P is false on this particular row, so it is by itself. I don't have to do anything to it. Q has a value of true, so I have to negate Q. S also has a value of true, so I have to negate it as well. So that expression, the expression of P or not Q or not S, is going to be false only for this particular row. I'm talking about the second to the last row here. Are we still doing okay so far? Okay. Now we have one more row to go. So for this one, we have all three variables being true, so that means they all have to be negated. So the expression that we want here is going to be the negation of P, or the negation of Q, or the negation of S. Keep pressing the wrong key because they're right next to each other. There we go. Are we doing okay so far with this process up to this point? We generate a truth table, we figure out the value of the expression that we want to convert into a CNF. We evaluate all the rows, okay? Each row is representing what happens to the value of the expression with specific values in the variables, okay? And then we ignore every single row that has a value of true from the expression, and we only focus on the rows that has a value of false. All right? And then for each row that has a value of false, we create a disjunction. In the disjunction, if a particular variable has a value of true, we negate it first. If a variable has a value of false to begin with, we leave it alone, okay? It is not negated. And that's how we generate, all of these things. Are we good so far? Okay. So I just yanked my our table here, so back in. All right, so with this method, what do we do next? Okay, because each disjunction is false only for the row that it is appearing in the truth table. But if you make a conjunction out of those disjunctions, then you end up with something that is equivalent to the original expression. So in this specific case, okay, in this specific case, my CN, oops, oh, what just happened? That doesn't look good. Undo, okay. All right, so the CNF that we are dealing with here is going to be a conjunction of the three disjunctions that we worked out. So in this case, it will be not P or Q or not S as one disjunction, and P or not Q or not S, oops, as a disjunction, and not P or not Q or not S as a disjunction. That becomes my CNF. So if I just kind of scroll up a little bit, you can see the final form of the CNF. The next question is, I'm looking at this and ask, is there a way to simplify this? The answer is, well, you can see all of them has a or not S in it. So the answer is, yeah, you can simplify this, but I'm not going to do it because the homework assignment only asks that you give me a equivalent CNF. It doesn't say that it has to be simplified or the simplest form of a CNF. Question?
Yes, so you made a shorter thing extremely long in hard to understand. So what is in the first two?
Because this is how we can apply resolution. Do you remember resolution? So in resolution, we are looking at, in order to see if resolution is applicable, we are looking at the conjunction of two disjunctions. The two disjunctions, one needs to have the negated variable of some kind, and then the other one needs to have the non-negative variable of the same one. And then once we identify that, then we can apply resolution. We end up with a expression without the variable that is negated on one side, but not negated on the other side. And then we concatenate the rest of the whatever is remaining on both of those expressions. Remember that?
Yes, we're setting the stage for that.
We are setting the stage for that. We are pre-processing the food so that it is digestible by the thing that we're going to deal with later. Questions? Any questions from people who are online? Okay, I don't see anything from there. Yep, go ahead.
We're turning one that was false.
Because that's how we can turn this expression here is going to give me a value of false when the variables have these specific values on each row. Okay, so think about it a little bit, okay? So if we just focus on this one here, this expression, this disjunction is false only for this specific row because it is only false when P is false, Q is true, and S is true. Then this disjunction is false. For every other row, this expression is going to be true. Okay. All right, so we're going to take a short break here because it's time to take roll because I want to see how many people who are participating online are still participating. So we'll go ahead and unhide this one. And there's a QR code already in here. So give me a second here to show you the passcode first. So the passcode is CNF, not surprisingly, all lowercase CNF. And the code is, I probably have to make this smaller before I can show the entire thing. Give me a second. There we go. So the access code, once again, is CNF or lowercase. Is that working for you guys? I guess we'll find out soon. It works. All right. All right, excellent. Yep. CNF, all lowercase. Conjunctive normal form.
There's also a DNF, right?
There's also DNF or disjunctive normal form. That is correct. But DNF is not useful to us because resolution only works on CNF. So that's why we're focusing on CNF. Righty. So we all good here? Okay, I'm looking at the, oh, okay, we got people confirming online that it's working, but someone said it's not working. So Andrea in Alexandria, can you, is it working now for you? I hope so. All righty. Okay. So we're getting back to our Joplin presentation here. So this is one method, okay? Now, is this method going to work well? I mean, it depends on, how quickly can you code, and generate the truth table and how many rows are false to begin with and so on and so forth. So that's one way to do it. But I can guarantee you one thing is this may not be the best method to use in exam 2. You can do it with a homework assignment, but since exam 2 is on paper in person, that may not be easy to do. Okay, so you might want to also try out the second method, which is by boolean algebra. Yes.
Speaking of exam 3,
It's going to be about 2/3 through the semester. I believe this is week 8. So
like 4 weeks away.
about 2, 3, maybe 3 to 4 weeks. Yeah. All right. So now we are going to talk about Boolean algebra. So we're going to do algebra here. And if I go back to the notes, I also want to show you where you can find all the rules for this kind of algebra. So there's a little discussion here of the general strategy, which I will apply. But there's also a link here to the laws of Boolean algebra and Boolean algebra rules. And if you click on that link, hopefully it still brings you to the document that I was reading earlier. Oh, no. It worked last time when I was here. There we go. There. So A or true is true, A or false is A and true is A or A and false is false. So in other words, I'm not the only odd person who choose to use plus to represent disjunction and multiplication to represent conjunction. Okay, other people do the same thing. Now, negation is a little bit different because negation is an over bar in this notation. Over bar is not easy to type on the keyboard, so I don't use over bar. Instead, we use the exclamation point, which is also what you learned in CISP440. So we have the commutative law of disjunction, the commutative law of conjunction. This one is De Morgan's law. This is also De Morgan's law. So those two are De Morgan's law. All right. So that's your basic algebra thing, okay? But let me apply algebra, your Boolean algebra, to solve this one, okay? Oh, sorry. This is in the propositional logic module. And let me see, it is in section 5.2. It's section 5.2. So if you look at section 5.2 is basically all you need to use for the homework assignment.
It's 20 points. It's just in here.
It's motivating you, right?
You won't feel that way.
It depends. I mean, it depends on. Okay, so we'll now deal with the same thing, but using algebra. Okay, so we'll go ahead and use copy and paste this. Okay, so let me copy and paste this first. Okay. And this time we're going to use algebra to solve this. Okay, so when you're using the algebra approach, the first thing you want to do is to deal with the implication. Oh, it doesn't. Okay, I probably should still do. Okay, there we go. I'm going to quote the entire thing, so this way it's not going to complain about your special symbols. There we go. Let's scroll the other side so we can actually see it. Oh, there we go. I don't know why those are all in italic. That is odd. Oh, because it's an expression. That's why. Okay. All right. So we're going to convert this now to. Okay. The first thing I usually deal with is the implication. So implication, you can get rid of implication because A implies B is the same thing as not A or B. All right. So does everybody? Yep. A implies B is the same thing as not A or B. That's one of the way you can define implication. Yes.
If we remove the implication, won't like the left side have like a not outside the disjunction?
Yep. So we're gonna have a not outside of this, and then we have the or with the other side.
Yeah, okay. Wasn't it like if you have a disjunction, a negation outside of the disjunction, it becomes not well formed, I think, or like in last lecture?
Well, this is using Boolean algebra, so it's outside of the well-formed formula discussion. Yeah. So we are applying Boolean algebra by hand. So in other words, we are kind of massaging the presentation of the data before we can use resolution as an engine to prove the theorem. So this is not using propositional logic. This is actually using Boolean algebra. Okay. All right. So are we good with how we got from the first line to the second line by the definition of implication? Okay. So now we look at this and go like, how do we convert this into a one gigantic conjunction? The first thing I would do in here is I know if I apply negation to anything other than a single variable, we do not like that. So I'm going to apply De Morgan's law. So in this case, De Morgan's law is going to be applied to this expression. So it becomes not P and not Q. Okay, so I'm going to type it here. So we have not P and not Q, and then the rest would still be the same. Are we doing okay so far? This is the application of De Morgan's law. De Morgan's law, generally speaking. Okay, let me just kind of point out what is De Morgan's law. So De Morgan's law. There are two forms of De Morgan's law. The first one is if you take the negation of A or B, it is the same thing as not A and not B. That's the first form. The second form of De Morgan's law says if you say it's the negation of A and B, then it's the same thing as not A or not B. So those are the two forms of De Morgan's law. Basically, if you see a negation of a conjunction, you can turn it into a disjunction with the negation applied to each component. the best way that I look at, okay, not the best way, but the way I look at De Morgan's law is quote unquote the distribution of negation. So instead of saying the negation of the result of an operation, you can now apply the negation to the components of the operation. But you have to change the operation because the negation of a disjunction becomes conjunction, the negation of a conjunction becomes disjunction, but each component is negated. All right, so once we have the Morgan's law explained, and we can get back to here and go like, okay, so what do we do next? By the way, this is a DNF, is a disjunctive normal form because the last operation is a disjunction and the components that we are drawing are conjunctions. So it's the opposite of what we want. You go like, oh man, that sucks. Well, yes and no, okay? Because we can apply one single step here and be done with this. It's called distribution, okay? So distribution, there are two versions of distribution in Boolean algebra. So let me add that to this portion here. So you can have, A or B and C. That becomes A and C or A, B and C. This one you go like, yeah, that looks familiar, right? Because if you look at or as the addition and conjunction as multiplication, that's the same distribution law that you know all along, right? There's nothing mysterious about this one. But in Boolean algebra, the opposite is true as well. So that means if you have A and B, the whole thing or C, then it becomes A or C and B or C. That works also in Boolean algebra, which might take some getting used to. So if somebody is thinking, that's just unnatural to me, I don't think that is true, Tack, I think you made a mistake. So in that case, you still don't need to trust me, right? The idea is if you trust me, if I tell you something that is not true, then we're in trouble. But by not trusting me, I tell you something and you just question, you try to say, okay, what if Tack is trying to trick me and tell me something that is not true? Then you find a way to prove it, right? So the question is, how do you prove this equality? Okay, let me use the mouse pointer here. So the question is, how do you prove this equality? Because it seems unnatural to you. It does not work in general algebra, but I claim, Tack claims that this works in Boolean algebra. So what do you do to prove this? Truth table, exactly. Aren't you guys getting tired of me mentioning truth table by now? If the answer is yes, that means you have been learning. If the answer is no, I go like, maybe I have not mentioned truth table often enough.
Okay, using this method to avoid truth table.
No. You use a truth table to establish the left-hand side of the equality is the same as the right-hand side of the equality. Okay, so another question. I know you guys are going like, no, not again. How many rows do we have in order to establish this equality in the truth table? 8 rows, exactly, because we got 3 independent variables. Okay, so now I'm going to apply this and go like, oh, okay, so I can apply the distribution here. So I can now break up not P and not Q. So not P gets to be ORed with not S, and then not Q also gets to be ORed with not S. And guess what? Now we have a CNF because the last operation is an AND, but the components that I'm ANDing together, each one is a disjunction, and the things inside each disjunction is either a variable or the negation of a variable. So now it is in CNF or conjunctive normal form. So this is done by using Boolean algebra. So do you want to use? Oh, okay. So here's the next question. It's like, so Tack, since you mentioned the trust thing, I don't think I can trust you because the CNF that we derived earlier looks different from the CNF that we see here. What is going on here? So what do you think? First of all, if you just want to say Yeah, the CNF from here looks just like a little bit more cumbersome, but it really is the same thing over here. What will you do to show that that is the case? That this is really just a longer and more cumbersome expression, but it really is the same thing as this one here. Truth table, yes. Okay, so somebody has to do a truth table counter in my classes. It's like, how many times the tag mentioned truth table in his class? Use a truth table. I mean, it really is that useful. Okay, so even for these two expressions to look so different, one looks a lot simpler, the other one looks kind of cumbersome. You can use the truth table to do it. Okay. The other way is to apply resolution, because resolution actually does apply in this case. Because you can see how we can have Q, and this is a not Q, so that means we can merge the rest of the variables. So you can actually apply resolution even within this CNF itself. But that is not needed for this homework assignment, because for this homework assignment, I just need you to arrive to a CNF that is equivalent to the original expression. That's all I need. So are we doing okay, or are there any questions? Yes.
So when do we know how to stop? When to stop?
We stop when we have a CNF. So that means you really need to know what a CNF is. Yep.
Well, you always get like a smaller like expression you a boolean algebra method or
Not necessarily. It depends on whether we do simplifications along the way. It also depends on the complexity of the expression itself. So sometimes you can end up with a lot of additional terms by doing it by algebra. But some of those terms can be absorbed. So there are ways to simplify those terms.
Do you consider constructions that we follow along to solve these kind of problems, or is this into?
It's algebra. So if you know,
Should be a set of procedures followed to arrive at conclusion.
well, one way to do it, I have a little bit of a guideline here. Okay, so let me get back to section 5.2. There's a little bit of guideline over here. So implication becomes the negation of the left-hand side or the right-hand side. If you have a or something else, then it depends on whether these two components by themselves are also just ors, then you're done. So there's a little bit of a guideline here. But for the most part, you just have to kind of figure out what are we trying to accomplish. So if you see anything that is a negation of an or, you definitely want to apply De Morgan's law. There's no question about it. If you see the negation of an and, also apply De Morgan's law, because we cannot have a negation of anything other than individual variables. So when you see a negation applied to a conjunction or disjunction, we have to quote unquote distribute the negation to the components inside the operation. So the De Morgan's law are basically it's a no-brainer. Okay. When you see a conjunction and then the result of the conjunction is or something else, you use distribution, because that's how you can end up with a conjunction with a bunch of ors. And then when you see something and something else, depends on whether it's at the top level already. If it's a top level, then you're good. And so on. I mean, I can show you as another example.
That would be great.
Okay, let's do another example. So this one came from the module itself. So the module comes with its own example, which is a little bit on the hairy side, okay, depending on which way you do it, okay? And I know there's an alternative way to do this that is not nearly as hairy, but this is what I call the scenic route. You want to get from, you want to go from San Francisco all the way to Los Angeles. You can hop onto I-5 and go straight down and fall asleep. Hopefully you're driving a Tesla, or you can use Route 1, right? You can use Highway 1 and enjoy the scenic route and the scenery. This is the scenic route. All right. So let's see if we can identify those rules that that is being used here. From the first line to the second line, what happened? Exactly. So we use the definition of implication to convert it into the negation of the R or Q. Okay, so this particular implication is changed to the negation of the left-hand side or the right-hand side non-negative. Okay, so that's the first one. So what happens between the second and the third line? De Morgan's law, very good. So we have a negation of an or. So we distribute, quote unquote, we distribute the negation to the components of the or, and then turn the original or into an and operation. So between here and here, it is just a simplification because double negation cancels out. So we have just R itself. So that's basically between the third and the fourth line. What about between the fourth and the fifth line? Between these two lines here, what did I do? It's distribution, very good. Okay, so we basically look at R and not Q as one thing, and then we look at P or T as another thing. So we distribute the P to one term, we distribute the T to the other term. So this is actual distribution. Very good. Okay. So after the distribution, what do we do? Look at the length of this line versus the length of this line here.
Another
It is
distribution.
Another distribution, exactly. So this is basically the same thing as a FOIL, okay? Because we have an and that has three components, or another and that has three components. So we end up generating what? 3 times 3 or 9 individual terms. But that's basically the same thing as FOIL, okay? You know, in normal algebra, you call that FOIL, which stands for what?
There's first, outer, inner, last.
Okay, that. You don't use the term FOIL, but you probably have applied that, right? Yep, so that's basically FOIL. So basically, you know, this R is ORed with this R here, and therefore we have R or R. This R is also ORed with this not Q, and therefore we have R or not Q. This R is also ORed with this T over here, and that's why we got R or T. And then we move on to the second component and do exactly the same thing. And then we move on to the third component and do exactly the same thing. So that's why we ended up with 3 times 3 or 9 individual terms on the next line. So once we get to the next line, we can do some simplification. So we look at this line here, and then we go from this line to this line, and we ask, okay, so what just happened here? It's another distribution. Now, between these two lines, I could have simplified, okay? So this is one thing I do recommend you guys to do, is to simplify as much as you can, as soon as you can do it, okay? I did not. What do I mean by that? What do I mean by simplification before you go any further? R or R simplifies to just R. Okay, so if you don't want to type a lot of things and be prone to errors, simplify that first. What else can be simplified here? Not Q or not Q can be simplified to just not Q, right? And that's about it, okay? Not a whole lot. And then this whole thing, this whole thing is also distributed using the OR to the not P. So now we end up with exactly a CNF. So if you are to turn in just a CNF, we are really done. By the time we get to this line, we are done with the CNF already. But it's a really kind of cumbersome kind of CNF, okay? So we want to do some simplification. So the first simplification that we do is basically what I just said earlier. R or R is really just R, okay? That's an easy simplification. And then we got a bunch of, this is another simplification where we have not Q or not Q. So this not Q or not Q becomes just a single not Q, okay? That's also a very simple simplification. And then we got a bunch of ones, okay, or truths. So where do those come from? We have not P or P, right? Not P or P simplifies to true, but true or whatever is just true. So that's why this one, simplifies to a true. The one right before, same boat, okay? Because we have not P or P, that simplifies to true. True or whatever is just true. So we get another true over here. Same thing over here. So we have true and true and true over here. True and whatever is just whatever. So true and true is just true. Once again, true and whatever is just whatever. So once again, true and true is just true. So I can now collapse these three truths into just true, but whatever true and blah, blah, blah is just the blah, blah, blah. So it just disappears. Are we doing okay so far with that simplification? Yep.
Just double checking, whenever you have just a true at all, even if it's just all of these.
Inside the disjunction,
I mean, it's all conjunction, you could just like get rid of it, right?
Yep.
Okay.
so in a conjunction, if a component in a conjunction is true, you just get rid of the true itself. In a disjunction, if any component in a disjunction is true, then the whole thing becomes true. So it's really handy, that simplification is really handy. And then from here to here, we just got rid of the three truths. Yep.
Before those got converted to points, what happened to not P or not Q or
What happened to the not?
not P or Q?
You mean this term here? It disappeared, right? So very good. Okay, so why or how can that disappear? So it disappeared because not P or not Q absorbs this term here. It would also absorb this term later on. Okay, so here's the mystery, okay? How can we do something like this? There's a, okay, first of all, how did we get to this not P or not Q? That's because of this, right? Because we have not P or not, excuse me, not Q or not Q, that simplifies to not Q. So your question is very good because you're asking, how come this term disappeared? Okay, so let me show you another simplification trick. It only happens when you're dealing with an and. So let's go here and take a look. Okay, let me get to here. Okay. So once again, I'm escaping everything. So this time we have a conjunction. One has P, whatever P is. The other one has P or Q, whatever Q is. I can just say that this really just boils down to P. The P or Q is useless. Okay, does that make sense to you? So first of all, does everybody understand what I'm trying to, what is the equality about? The equality is about P and P or Q simplifies to just P. Now, P itself doesn't have to be a single variable. It can be a huge, big, long, complex expression, and so can Q. But does that make sense to you? Now, if it doesn't make sense intuitively, what do? Exactly, truth table, okay? So you can use a truth table. This time we have two independent variables, and you can verify that the expression P and P or Q is exactly the same thing as the expression P by itself, regardless of P, what P and Q are trying to represent.
What happens if we distribute?
Hmm?
What happens if we distribute P to P and Q to? So it can be P.
So if you want to do the distribution here, then it becomes P or P and, excuse me, it's P and P or P and Q. And we are claiming that that is the same thing as just P. So this part here is the distribution, right? Yeah, we are using distribution to, so just thinking whether that makes sense or not. Yep, I think that makes sense.
So P and P is true and it's regardless of the support, so you take those P.
So, okay, so now we have three equations that are all supposed to be valid, which means if we were to use the truth table approach, we can prove each equality individually. But does it make sense to you intuitively? That's the other question is, do you get quote unquote a feel of the equality? Let's take a look at the last one. Okay, the last one says P or PQ is just P itself. Does that make sense to you? In other words, if P is true, regardless of Q, don't you think this disjunction is going to be true? Okay, that makes sense, right? What happens when P is false? Now, if P is false, then we have false here. But since this is a conjunction with Q, that also has to be false. So it makes sense whether P is true or not, that P P or P and true, P and Q has to be the same as P. So you can apply the same kind of reasoning over here. When P is true to begin with, then P itself also has to be true, right? What about P or Q? If P is true, then P or Q has to be true. Because true or whatever is true. What happens when P is false? If P is false, then P is also false. It doesn't matter what Q is. Q can be true, it doesn't matter because it is connected by a conjunction. So that means if P is false to begin with, then the entire conjunction is going to be false. So from that sense, it also kind of makes sense intuitively. But you can also use a truth table to actually see that every single row is the same, regardless of which expression you're using on the two sides of the equality. Yes.
Oh, is there a name?
I'm pretty sure there's a name, but I cannot remember what it is. It's probably some kind of absorption. I'm very, very bad with names. So you can probably look it up. Ask ChatGPT. That's it. That's what it's good for. All right.
It's getting tedious to Google things these days.
Hmm?
It's getting tedious to Google things.
Well, that's why as soon as ChatGPT 3.5 was released, that was a high-level urgent meeting at Google's headquarters because they knew right away that their position is getting challenged big time. Yep.
This is actually a good time for Microsoft Bing because no one used it, I think, and they implemented the GPT in their
Yep.
AI system.
They actually went ahead to use ChatGPT 4.0 when everybody else were just playing with 3.5. Yep. So they were actually one step ahead of the game. Yep.
ChatGPT says it's called the absorption.
Say that one more time. Sorry.
ChatGPT says it's called the absorption.
Absorption property. So I was right about it probably has something to do with absorption, right? Yep. Yep. Thank you. Yeah. Thanks to ChatGPT as well. So ChatGPT has the collection of all the accomplishments of humans, but also all the not so great accomplishments of humans as well, because it's all based on what we have created as humans, right? So it's kind of interesting because if it's not trained correctly and we just collect all kinds of crap like the entirety of tweets from everybody and use it to also train the ChatGPT, the result would not be very useful. Yep.
I've asked it to cite its sources sometimes, and it makes some.
Oh,
Yeah, so like I've asked them for a book on logic.
Yeah.
And they came up with like 5 books that there were no ISBN number version. And then when you tell it that you couldn't find it, it's like, oh, I'm sorry.
I see. Yep.
You know, it's GPT-4 has data past like 20.
I think so. Yeah, I think they have incorporated more data compared to 2 years ago, because I think ChatGPT 3.5 used data that were 2 years prior to the release. So that's 2022 because it was released in 2022 in November, if I remember correctly. So that means ChatGPT 3.5 was only using text information online up to and including 2020 November-ish. Yeah, I think 4.0 is using some additional data. If you guys want to do some fun stuff with ChatGPT, you can also look up, this is funny. I know it's not related to the class, but you need to do something to pass time, right? So, so that's ChatGPT gaslighting. There's an entire conversation of how to gaslight ChatGPT. Yeah. So I just thought, this might be of interest to those of you who are just getting bored with the homework assignments. Like, oh man, do we have to do this? I'm just gonna go get some entertainment here.
Polluting the open AI. Polluting ChatGPT with false information.
Yes, intentionally. Not that we are not doing it already. This one is intentional. Yep.
Intentional.
Yep.
Many of us are out there doing it unintentionally.
Yes. All right, so we are only one little step away from finishing this, but you got a question. Go ahead.
I was just gonna ask, it's not related really to the class, it's more about chat GPT, like we need to see like the South Park on it. Yeah. Yeah,
Yeah, it's really interesting. A lot of organizations are now accepting submissions of creative work, that are generated by Chat GPT, including screenwriting. Yeah, the society or however they call the organization, they are now accepting screenwriting content that's generated by Chat GPT. So that means my lectures would not look too bad. Yes. Yeah, some kind of organization, where screenwriters belong to, like a guild or something. Yeah, they are now starting to accept creative work generated by ChatGPT. Anyway, we only got one step to go. How do we go from here to here? I mean, this looks so long, this looks so short. So it's using the absorption thing, because we have not P or R here. So that can take the place of this thing here, the place of this thing over here. And then we have not P or not Q, which can also take the place of this thing here. So that's how we can simplify the entire thing down to not P or R and not P or not Q. All right, so one little thing, since we got 2 more minutes to go. So as you are deriving, okay, how do you know that you did not make a mistake and you end up with an expression that is no longer the same as the one before? You can use a truth table, yes, but you can also use the program that I wrote earlier, or the equivalent, equivalence of this program here. So what you need to do is to have the original expression expressed here, and then also add one more column of the one that you are currently working with. So that means if you see the original expression returning a value that is different from the expression that is the result of the derivation on even one single row, that means you have made a mistake somewhere. So, but it is not, it's doable, okay? This is one way to check your own work to make sure that your derivation steps were all correct. But I'm not saying this is going to be easy, right? Because every single step you have to convert your expression into C++ syntax, unless you have a way to mechanically convert the notation that I expect and convert that into C++ syntax. And that is doable as well. Now that one, you probably cannot do in 15 minutes. That might take a little bit longer, exactly. But a parser is not difficult to write. I mean, you can potentially do it. It's just not easy. But you can always just manually do it. Okay, just kind of spot check. So let's say your derivation has 15 steps. Okay, you can do it on step 5 before you move on, just to make sure that you're not going to waste your time. By the time you get to step 10, you can check again. But if you do spot a mistake, it's somewhere between step 5 and step 10. So you only got like 5 steps that you need to double check by hand. And then by the time you get to step 15, it looks like a CNF. Check again, make sure they are all equivalent. Okay, so you can use mechanical ways to help you spot check the derivation. All right. So some of you might have questions as you work on the homework assignment. I do have office hours. Okay, you have office hour. I mean, I can talk a little bit after class today, but if you look at if you read your syllabus, I do have office hours on Thursday and Friday, and then also on next Monday, we can talk about it again. This is due next Wednesday. Okay, so you got an entire week to work on it. I would suggest that you guys get started early. There's no penalty for finishing early. and starting late does not change the amount of work either. Says the person who procrastinates the most. Yes. All righty. Okay, so this is all done. I will upload the recorded lecture online as soon as it's available. And I'll see all of you, some of you, next Monday. Have a nice weekend.